us there. And we had our comparators. I don't know whether I should redraw them. We had a bunch of them. And I guess, as I promised, I put them we are filling in with the right corner. So, and the corner, and then eventually we have converted our analog signal into 3 bits. B0, B1, B2, these were our output binary card, B0, B2, B1, B0. And these were errors. R over 2, R over 2, then R. These were going to the earthing, so they were invalid, non-invalid. And then we had subdivided the voltages, the reference voltage was subdivided into 8 subdivisions. These were D8, from D8, D7, D6, D5, D4, D3, D2, and then D1. This was comparator 7, comparator 6, comparator 5, comparator 4, comparator 3, comparator 2, comparator 1, and comparator 3 now. And this was the priority encoder. Okay, so that's where we stopped at. Now we try to say a couple of things. things about the operation. So the sub-reference voltages, VI can be given or are given by 2I minus 1 over 2 to the power n plus 1 times, okay, there adds a factor of the reference voltage where the I is equal to 1 in the steps of 1 up to 2 to the power n, and n is the number of bits. N is the number of bits that we are trying to convert our analog signal to as the process of converting our analog signal to a digital signal. And this is the same as to have 2I minus 1. And then we have V reference over this case we have over 16, which is the same as 0.625 into the 2I minus 1 times the reference voltage. How about what is all about the comparators, or what do we need to know about the comparators, those operation amplifiers? We have a level detector, whose output changes when the input exceeds, or falls below what we said by. So you said the programmer, the designer of the ADC would choose to make it detect and have a level detector whereby either below or above a given value, then we would have a change in the output. E.g., for example, if we have still got this diagram for me, I don't know you got it on the video. We got it. Are you here or you just came because I have to go? So we have the comparator, the operation amplifier, inverting, non-inverting. We have the V-in. Remember, the V-in is at the non-inverting, positive. All of them are connected to the non-inverting here. By nomenclature, where you put a dot like this, it means that it is a connection. So they are all connected to the non-inverting. That's why, much as now it is down, but here the class was up, the non-inverting. You just need to know that there is no difference. The V-ref was at the inverting. All the reference subdivisions, these voltages from V8 up to V1 are going into the inverting terminal of the operation amplifier. The V-in, this input here, is all going to the non-inverting. So if you So then we would have a graph, a level detector, whereby we would have falling below a given value and rising above a given value. So this is Vref, and then we have Vin, then we have, no, this is V out, and then the reference voltage. This is the reference voltage, and then we have the plus VCC and minus VCC. This is rising, so the other one is falling. So, or we could have the falling one, still with our nomenclature of the comparator having the input, the Vin on the non-invariant and the Vref on the invariant terminal, and then we end up with the graph, the V output, the output, either, so it was either rising, changing when the input exceeds. This is exceeding the preset value, or falling below a preset value. And we have our Vref, and this is Vin, and this will be our minus VCC, and this is positive VCC. VCC does not mean that it has to be on the other transistor which you, whatever, any supply that you are using, we do it as a VCC. We have this encoder, so we can write a couple of things about the encoder, which is the priority encoder, and see what is going on. So can you do this quickly? Because I need big space. You all see me with the humble eyes. Why? Didn't have lunch? Just thinking about it. What exam do you have first? There's no exam for you on Monday. No, it's in education, not in physics. Yes. I don't know what you do outside here. Why did I know? I don't want to know. Neither do I need to know. So primary encoder, the priority encoder, it has it has 2 to the power n inputs and n outputs. N is a number of bits, okay? So if we have 3 bits, if we have a 3-bit encoder, we are saying that it will have 3 outputs, because that's the end and the cutoff. To get your thing, I don't have time to keep your stuff with me. and it has 2 to the power n inputs. 2 to the power n would be the same as 2 to the power 3, which is 8 inputs. So that's why we have 1, 2, 3, 4, 5, 6, 7, 8. If it is a 3-bit, it would end up with 2 to the power n comparators for the inputs. And it would only output 3 bits because it is a 3-bit ADC converter.
I had to just switch that place.
You are forgiven. So then we got the, it assigns priority. It assigns priority. It assigns priority to the input lines. To the input lines. So that when multiple requests are made, the encoder produces the number of the highest priority request. The number of highest priority requests. E.g., if we have, I am going to remove this. I guess now you have an idea of how it looks like. Your eyes closed. But we want to draw a table of all these.
Excuse me. Yes, is that yesterday?
Yes, it was just a review of yesterday's.
This part which is new.
This one here. Yeah, many. I put this, there's another one. And some other words. And some other words. So you are late, you are really late. But you are forgiven.
I'm sorry.
You already forgiven. So I want to keep this so that we compare the two easily. So I will use this other side since you have written this thing. So it gives priority to the requested start. So I still want to have the C3, C5, C6. And then so e.g., we look at an 8 input, which ends up having 3 output binary card. So an 8 input priority encoder. We got a table, and then we shall have the comparators in a sequence. So we got C7, C6, C5, C4, C3, C2, C0, and then we shall have our outputs here as Y1, no, Y2, Y1, Y0, and then finally have an equivalent in base 10, the decimal equivalent. So we start with when we have now input. No input. Now when our V in is here, we have nothing. So that's when C1, C2, sorry, C7, C6, everything 0. do we get as an output? We got nothing. Because now we got no bit. And that gives us our 0 in decimal. So now we switch, we let this one, do I have up C now? So we now make this one input 1. Give it an input. So 0, 0, 0, 0, 0, 0, 0, 1. Like that. So until when all of them are switched on. So when I don't know how far we shall go. So 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, then 0, 1, 1, 1, 1, 1. And then we shall have the bits. So these bits are easy to have. So it's 0, 0, 0, 0, 0, 1. So 1, we shall have the first 4 zeros, then the next one 1. So 0, 1, 0, 0, 0, 1. Then you wait, I finish so that you see why it is. So 1, 0, 0, 1, 1. Then, am I in the same lines? This one should be straight here. So this is 0, 1, 1. Then 1, 0, 0, 1, 0, 1. 1, 1, 0, 1, 1, 1. You see why we can't have this one reaching a level, that state of being 1, because we will have exhausted those combinations. We can't have any other combination. But 1, 1, 1, 1, it's done. That's why it is limited to eventually giving us only these 3 bits. When we have put a bunch of 8 inputs, that's why it is tough. Convert. You need 8 inputs just to produce 3 bits. When you are converting from an analog, digital signal. The rest is how you conceive it in terms of the understanding of how these switchings happen. In the previous one, we said we use the FETs for the switches. After using FETs for the switches, the resistances for the ladder method, the resistances are etched on a thin film and used in the circuit. So you see some thin stuff. You don't know what is going on, but then actually you have a whole bunch of stuff. So flash converters may vary. We are looking at the fastest. This was the fastest of the ADC, because we stated the 3 of them: flash or parallel converters, successive approximation method, and reduced form. And we have started with these comparators as the flash. So these flash converters may vary from 4 to 10 bits. From 4 to 10 bits. I have forgotten this. This is 1, 2, 3, 4, 5, 6. 7. Is 1117 in base in binary?
Yes.
Yeah. So this is the decimal equivalent. This is the binary equivalent. These are our inputs for the comparators to be able to give us binary output. You can imagine now 10 bits. How many comparators do you need to produce 10 bits? it's 10 bits. So if it is 10 bits,
9 by 2.
n is equal to 10. So that means you need 10, 2 to the power 10 comparators. And then in order to be able to produce 10 outputs. And so it's speedy, it's one of the speediest, but also to implement it is a bit tough. And what does that go with? 10 to the power 10 is how many? Yeah, so that now culminates into the cost. The cost of these comparators and plus all these resistances that we are using. So the cost and the size. So the size of your comparators by the time you take 10 bits. So the cost and size being the limiters, being the limiting factor. And the reason is because that's why I didn't want to have this, because of this kind of architecture. It can't even fit on the board. So how will it fit in the on the circuit board? Unless if you change it to, that's why we struggle to make sure that we get the IC chips. And you have seen them in the lab at least. So the speeds range from about 15 to about 300 megasamples per second. The MPS is the mega samples per second. I'm sure you are used to the megabits per second or megabytes per second. Whatever you are we good?
Yes.
Yeah. So we got the second one, which is slower than this one. And this is the successive approximation of successive approximation convert. They are the same whether in the United States, whether in China, whether in the United Kingdom, they are the same. They do the same thing. You carry the same phones that the Americans are carrying. But when it comes to your hard work, you say this is Africa. This is the technique used. This is the technique used in most ICs, in most integrated circuits. The principle is that the analog signal is repeatedly compared with the number of approximate voltages, generated by the digital to analog converter. have you covered the Newton Raphson method?
Yes.
Whereby you put in a variable, then you follow the chart until when you have the difference between the one you got and the previous one being so small that now you say, this is the number. But it is a hassle. And that's how life is. Life is simple if you can make choices that they are approximate to the right ones. You can't gamble everything and when you are perfect. So you push in input A, then you calculate the difference is large. Then you say the smart people are those who put the first guesswork comes with the difference. Come out with the difference which is minimal, and then they say yes, I got it. Even if you put things don't work, you try again, things don't work. So you keep trying all the time. Diagram, we have a comparator. If you allow me to draw this thing so that you do at once. And then we have a successive approximate SAR here. And then we have, we said we get the voltages generated by the DAC, the DAC. So we have a DAC here, a digital analog converter. And then it keeps, so we get some values. And then these values, we take them to the, so we have this bit here. Then we have this bit here. This is, so it moves from B0 up to Bn. And then we have start. And then we have status. This is start, status. These are output. This is the output code you get eventually. But whatever we get from this DAC, the analog signal is repeatedly compared with the number of approximate voltages generated by the DAC. So we get the value from the DAC and we input it here. And then we do, so we keep comparing the input, the analog signal which we are inputting, we keep comparing it with the values from this digital analog converter. And this is V2, and then this is the comparator, and this one connects into V1. Of course, here we trigger it with a clock. Remember, give it a pulse so that it can give us that input values, those input values to be able to be converted. And then the SAR stands for successive approximation register. So this is our register, which successively corresponds with the clock. So when you start, it produces the signals, and then this signal gets converted. We use a converter. It converts this signal, gives us a voltage V2, which we keep comparing with Vn, and then we get V1. And the process keeps coming on as we produce these bits. And this was a 4-bit converter, what would be the story going on? E.g., if we consider a 4-bit digital analog converter with a full-scale range voltage, of about 16 volts, and an input of about 5.7 volts. Then we would have the I will draw something here in this space, but I want to first draw the clock. So I have the square wave for our clock. I don't know how many I gotta put. 1, 2, 3, 4, 5, 6, 7. How many are these? So 1, 2, 3, 4, 5. I can add one here and one this way. Or I could have reduced it. So this is our clock beat, our clock pulse here on the successive approximation register. And so the start, we have a rising, these are rising parts of the clock. Whenever you have a rise, then that will be fall. Then we have a T0, T1, T2, T3, T4, up to T5. And then we got the start. So at the start, we keep it at T0 here. So we have a pulse here for the start. So we go, I hope you, so how many do I got? 1, 2, 3, 4, 5, 6. I'll have to draw the 6 of them. Then at T1 here, so maybe I first put them like this so that we got the so once we do start, then we start producing these bits. We start producing our binary stuff. So the first one, the B2, will be up to the T1 here, and it will go cover these two. So this is, make sure you draw it with a good amplitude. I I am trying to make sure everything fits here. And then for the, so this is bit 3. It's a 4 bit, so this is bit 3, not bit 3. And this is the most significant bit. And then I'll go to B2. B2 will be at T2 here. And we'll go this way. I have, this is B2. B1 will be at T3. T3 is here. Then I have, this is B1. Then B0 will be at T4 around here. This is B0. And then what will be the status? What will be the status of our converter? The status will be that at T0 here, we have a pulse up to where we stopped going, so it will go up to T at the end of, so at the rise of T5, it will forward. So here, up to here, and then it goes out. And here we shall say that it is ready. It is ready. Let me see how many. T5. That's the rise of the fall. The rise of T4. Yes. And then it's busy during all this time. It's busy during all this time between here and here. That one is it's busy doing conversion. So this is conversion time. Conversion time between here and here. And so you can have a reset. So what I wanted to draw here, which I dumped, is you have remember the V2, which we have to take to compare with the V in, is the V2 here. And then this will be the time axis. And then at the T1, at the rise of T1, so we have 0 at the rise of T1, we get a value. Then at the rise of T2, we get a pulse, fall pulse, our pulse falls. Up to T3 goes up a bit. And then we'll go up to the rise of T4. It goes down a bit, so keeps changing. I don't know whether I'll be able to do that. So this is 8, 6, sorry, 6. Then you have 5 and 6. And this is when V2 is 8. Anyway, if we receive the result of this here, I don't want to rub this so that you see this result here. It that we have the B3, B2, B1, B0. This is for the code, for the binary code for the 4-bit. There are 4 bits, B0, B1, B0, B1, B2, and B3. So this one is the same as 0, 0, 1, 0, 1, which is approximately about 5 volts. In general, you have to add a correction. The correction is added. I don't know whether it should be in general, but maybe it could be in practice. You have to add some correction to be able to use this. Anyone having issues with this diagram? How it flows? This, I don't know whether my level is, I was trying to look. This is the clock here. And then this one here, the first one, this one here, this pulse here is for the start. And then the beat, you start getting the beats coming out of the successive approximation register. Then you start getting the beats. So this is slow, but we have the slowest. The slowest is the dual slope in a grading converter.
Some of these peaks.
Okay, so we this top here. Yes, we are looking at we are getting these peaks here depicted on this. This is like, you can see this one here is this one here, and then we have this one going for this, and we have this other one going for this, but this one is to show us the start, the status of what is going on. It is conversion here or around here. Like, have you ever done the calculation, like integration of using a calculator? And then you just sit back and relax, and it is busy, it keeps blinking, blinking, then finally gives you the answer. Yeah, so, but I could, check online to see whether you can get a better diagram that picks out stuff. Just want to finish. The last one, slowest one. How many marks will you learn? Minutes will you learn me? 0. You have a test at 3.
So you are saying that in the test you don't learn.
Where is Sewu? You can imagine I gave Sewu for 4 hours. So you cannot accuse me of, and in the lab I always give you as much time as possible. Wednesday is supposed to end at 6, Friday is supposed to be ending at 7, but I always let you just come and say, we are tired, come and lock your damn lab. So, have a nice day. Dual slope, in a very Next time I'll be quick so that I teach these things when people are still interested in studying, not when they are thinking about exams. Not when they are thinking about exams. So I'll try to be faster probably next academic year. The principle behind this is that it measures the time taken. Charge a capacitor, and then converts the time, or let's be nice and say converts this time in a digital word. Sounds beautiful. Just make sure that it charges up a capacitor, measures the time it has taken to charge, then converts this amount of time into a digital word. So we have V in, and so we have a chance of, so this is V in, this is V ref, and then we have a two-way switch whereby we can charge. So we have a two-way switch through the resistor R, which will give us so we can send this now to our comparator or operation amplifier, and then we have a capacitor, and we have a switch, so we can bypass it. We can discharge this capacitor or bypass it, and then this output here is sent through another comparator, and then the output of this comparator, we try to get some control out of it, I mean some information out of it from the control logic. And then this control logic, we have to kickstart it by giving it a pulse from the clock. We have to start the process, and we have to be aware of the status. So this is the start, and this is the status. And then whatever comes out goes through a binary counter, which will count the time the capacitor took to charge and makes it a digital word. So this is a binary counter. This binary counter eventually gives us the word, which is Bn-1 up to B, from B naught to Bn-1. If it is a 4-bit, you can only go up to B3. That is Bn-4 -1, which is B3. If it is a 5-bit, you go from B naught to B4. And so then we have this grounded, and so this is also a comparator. This is switch S1. This is switch S2. This is we are charging. So this is non-inverting. We ground it. And then this is capacitor C. This is VT. And then this is V naught T here. You have the clock. This one is this circuit here, if you remember, this is the integrator. The circuit when we were having the different circuits of the operation amplifier, a differentiator, an integrator, and so that is the part of the integrator. I think I've leveled everything, and now I can say that the V out, the V naught T, this output voltage here is the same as the same as 1 over RC minus 1 over RC integral of from 0 to t, where t is the time of charging, dt, dt. This is AC circuits. The timing diagrams, is that we give a start. So this is a start, and then it will be, the status will be that it will be busy for some time until it is ready, and during all that time it will be busy. After that will be the status, and then we can draw the voltage versus the time. So the V naught T is minus, so we shall get it as we have T, and then we have delta T, this will be minus VF. This value here. And this V naught T is this time, this voltage away from the integrator. I'm left with 2 pages, so don't worry. I see some of you, and is this man seriously going on, because he said, no, it's already, I'm already 5 in your free time, but I just have 2 pages so that we stop at the end of the course. Like 15 minutes, Yeah. So, I also can't wait to stop, I can't wait to end, and tomorrow is not a big deal.
Have a practical tomorrow.
It's okay, practical is okay. You will do your stuff. It's your business. I'm not the one who will do it. But I want to finish this. In general, is that I don't want to really mess you. I don't like hurrying up people just because I want to finish. Learning is a process. Every day has its own experiences that makes you remember what you learned. Otherwise, people would learn things in a day and then move on. So, just a few statements to write, and then look at the transfer function of the DSC and the ADC, and then we put ground rules for the exam, and then I spot for you for exam, and then we end. Yeah, I'm gonna spot for you.
Okay. Yeah. Proceed.
Now we can
Start with that. Can start with
I want to do up to 7, eh?
No, can start with that.
So you see, I know how to make you give in willingly. So I wrote the diagram, but if you can refer to it, if S1 is momentarily closed, if S1 is momentarily closed, then that means that to reset V naught to 0. So the S1 is the one which bypasses the capacitor, and when you bypass the capacitor, you now reset to 0, because there's nothing that you will be getting at the output. Now S2, if it is switched to Vin, Vin was the upper part. So if it is, this one was Vref, this was Vin, and this is the switch. The switch this is S2. So if the S2 is switched to Vin, and simultaneously counter is not running, like you got no pulse there, the stellar signal set to busy. So after this time t here,
counter is not what? Rising.
counter is not running. This is running. So after time t, this time t here, halfway within a busy period, determined by the counter, switch S2 is turned to minus Vref, and simultaneously counter is reset hello. Hello? 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 You are doing a practical. Are you done? Yeah, you can take a break. I need some confidentiality. Then you come back in about 30 minutes. I haven't seen you touch any apparatus, so you can go do your compilation somewhere. I don't see any apparatus on. I gave them freedom to do whatever they do, but now they want to compete with me making noise. So I exercise my rights. Spontaneous counter is reset, and then set running, and set running to determine time, this time here, this delta t, to determine time delta t taken for V naught to become 0. We said V naught becomes 0 when we bypass it with the switch. So V naught t would be the same as minus t over RC into 1 over t in from 0 to t V in t dt, which is the same as minus t over RC V in, the amplitude, whereby not the amplitude, average. V in is the average, the bar is the average of V in over the time t. Or minus V ref is equal to minus T over RC V in. Let's take as equation 1. And for the positive going ramp, positive going ramp means one going up. So for the positive going ramp, we V naught dt would be equal to minus V ref over RC, which is equal to minus V ref over the this period of time over which the time taken for V naught to become 0, which is the delta t. Or we can say that RC, remember the charging time is the same as delta, and then we take this as equation 2. From these two equations, from 1 and 2, then we will have that the average Vn will be the same as the delta T over T Vref. Bonya and company, for you are just seated looking at me. You are like, you hustle. You hustle, it is your business. They are saying that I'm just looking at you. You hustle.
He's waiting for the summary.
They are waiting for the summary. They are like, you hustle. You are paid for it. You just continue hustling. All along I've been looking at you and you're like, yeah, hustle. You write. You have the time, you have the energy. Continue writing. Well, I can use Uganda since it is the last day. Mwesigachi. But we are hustling for you, are just there. When I was explaining something here, you were like, you were looking at me like, you continue suffering. No problem, on the 17th, it is the Saturday, I'll also be here. And I will use this room, I think. I'll be just here, I'll be looking like this. It's a Saturday. So this is equation 3. You are very interesting. So if T corresponds to the count, remember T, the charging time, is the time that we are using to produce a binary word, a digital word. Okay? So if T corresponds to a count, so if T corresponds if T corresponds to the count, if T corresponds to the count,
I hope when by the time I come back they will have put a nice board also here so that I don't have hassle.
Count and this count number equaling to summation from I equal to 0 up to n minus 1 of the VI 2 to the power I bit. I mean bit I. Is it bit I or I bit? And then for delta T, that part here, corresponds to n equal to summation I equal to 0 up to n minus 1 of BI 2 to the power I this should be, if I do this, it looks the same. So if we just put a prime here, whereby n prime so where n prime is less than n, then we shall have that V, the average V in will be equal to n over n naught V ref. It's important for you to get these notes because these notes are not only for the exam. You sooner or later you will be a big person. And then you need to have a reference. You need to have something to start with. Yes. This one here. Negative. If I consider 1 and 2, then I get delta T, V ref, I don't understand. I don't understand where the negative.
In equation 1, you have a negative V ref. Calling it T over R.
No, not equation 1. Equation 1 is this one.
Yeah,
Okay,
yeah,
here,
it's
yes,
one.
okay, fine.
Yeah. Then equation 2, we have R dt. Then comparing 1 and 2, we are substituting for R equaling to dt. Then the negative should remain here.
So we put RC good, so it should be minus delta T
Yeah.
over T
V ref.
V ref. If you say so, you will check properly, but I don't have it. Minus V ref over delta T. I'm trying to see where the
Because you are comparing the denominators, which are positive there, to conclude the answer with delta T. And in equation 1,
you find out. Okay? Same picture. See you. So I'm left with you check the arithmetic. I mean the arithmetic. I don't want to do anything. So finally, not finally, but on this part, if T is chosen to be the full scale, if T is chosen to be the full scale, counter, so let me use the full scale count, then n naught will be equal to 2 to the power n minus 1. And if we choose V ref equaling to 2 to the power n minus 1 volts, then we would end up with V in, average V in output. So what are the properties of the counters? What are the properties of the counters? Properties of counters. Where is Stephen? Together. Accuracy of a counter. Accuracy of a counter is independent of the components. Is independent of the components. Is independent of the components, the resistance, the capacitance, or the clock frequency, or the clock frequency. You can see equation 3 to see whether it has any relationship with that. I mean with those. The average value of the input voltage Vin is converted thus averaging out the fluctuations. The fluctuations in the signal over the time t. For example, in AC circuits, the reason we do average is that we know the signal is one point positive, another time it is negative, so we average to get a positive value by making sure that we don't deal with the other negative part. So it's like we take care of whatever went down and went up, and then we square. That's why we are looking, for example, at an AC meter. We take the reflection being proportional to the I squared over 2. So you first square to make sure there is no negative in your value, but then you are squaring. The squaring is to remove the other negative part, but now you have to divide it by 2 to take care of that. And so my last page, which I should have just posted on Where, is the transfer function. I'm very excited that with all the circumstances, with whatever we've done it, we've finished. I missed 2, so this one I've compensated. The other one at the meeting too. But remember, we also missed 2 Thursdays, isn't it? While doing tests. Other people put tests during lunchtime, that's why they do not take away their time. But for me, I was using the whole 1 hour for the transfer function. The transfer function of a converter, the transfer function of a converter is the graph For a digital to analog converter, VIN consists of digital words because we are converting from digital to analog. For analog, for ADC, analog to digital converter, VL is the one which consists of digital words. Now, we just take a case of a converter which is a 3-bit and then see how the transfer function goes. Next semester I buy my own job. E.g., if we take a case of a 3-bit DAC and ADC, then we have so we have in the steps of 0, 0, 0, 0, and then we have 0, 0, 0, 1, 0. This will be 1, 1. Are you able to see? Because the steps, I put big things, steps, I will finish the whole board. And then this is 0, 0, 1, 0, 0. Then we have 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1. And then the other one, the last one is 1, 1, 1. Let me see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Where are the others? 0, 0, 0, 1. 0, 0, 1, 0. If it does, if it gives me headache, I'll just post on the web. 0, 0, 0, 0, 1. What would make sense if they just walk out like that? He's tired. Math lecture. It's a math major. So what? If he's a math major, so what?
It's just come on the test.
I just come out of the test. Hey, you were with him?
Yeah.
But mathematics is very simple. Yes. I never used to find any problem with math. I'm serious about that. It is physics where you have to read so much. So we got this. This is for the dark, for the DSC, and we say that for DSC, the V in consists of digital words. So this is our input. These are our digital words here. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1. The order, you will check out the order. And then you will have these steps. So I will have this, I will have this, I will have this, then I will draw the line, hopefully nicely later. I'll have this corresponding to this corresponding to this corresponding to this, I'm done. So I will have the steps, these steps here. And then you have these values here for the different amount of the output. Yeah. So this is the V out in volts. And this is the stepped function. Stepped function V out. Then we do the same for the, this was the input. For the ADC, what is the output here? The digital words. So I just, I thought I could use the same graph since everything is almost done. So if you finish that, then you let me now change the input, the output, and then the input this way still remains this way, and then we make the final conclusion. So it's 0, 0, 0. But are they 4 or they are 3?
Yes, supposed to be 3, that's what it is 3 bits.
It's a 3-bit, so I don't know why I was hustling with 4. So just to make sure that my eyes duplicate digits these days. They give me an extra digit. If I wish that was money, I would see money and add another 0. So it's supposed to be, we have a 0, 0, 0, 0, 0, okay? Yeah, so it's 3 zeros, and then the other one would be 0, 1, 0. Then the other one would be 0, 1, 1. Then the other one would be 1, 0, 0. Then the other one would be 1, 0, 1. They each 0, 0, 0. Then 0, 0, 1. 0, 0, 1. Then after 0, 0, 1, we go to 0, 0, 1, 0, 0, 1, 0. Then 0, 1, 1. 0, 0. So it is 0, 0, 0, 0, 0, 1, 0, 1, 0, then 0, 1, 1. Then we go to 1. So we go to 1, 0, 0, 1, 0, 1, then 1, 1, 0, and then 1, 1, 1. this now to a dark, one, so it shouldn't be a big problem. We now do the we just now label this one is our output here, which are the binary digits. So these are output, and this is ADC, and now these ones go here. So this will be 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then this one will be 1, 1, 1. These ones now will be in the middle here. These ones now are not labeled here. We don't have any digital words here at the V-in. We have V-in. For example, for the successive, we have V-in, and then we kept comparing with the output. So this is the V-in. This is as a function of the full scale range. So, my last sentence. This is my last sentence. I don't know whether sentence or sentences. My last sentence. The function is stepped. Okay, stepped means that it is made, it is in these steps. Because input voltages, V in plus or minus this significant bit either side of the quantization, quantization level have to have the same gigawatt. So there were sentences. The number of quantization levels, the number of quantization levels is 2 to the power n, where next semester, those who will be interested, we shall do electronics and instrumentation. We now shall look at how to use these electronics to make instruments. And I think on mood viewing you did look at the robots. So we shall have one of the practicals as a robot, assembling the robots. Those robots, basic. They already have downloaded programs, so you just assemble the pieces. Once it moves, then you get your marks. There is no cheating. If it doesn't move, then you get 0. So the instructions are always put on Mwere, and after they are put on Mwere, you go through them, you assemble the damn thing, then we run it. If it moves, then you get your 10 out of 10. So in summary, there are a few things I want to say concerning the upcoming exam. Everything I've told will come. So that was the spotting I was talking about. Yeah. From when we started. But there are 2 sections which I didn't teach fully. There was a section of AC voltages, or AC voltages, AC currents, transient currents, and I just flipped over them by showing you the DC and AC generators. But then it's more to do with the part which you covered in electricity and magnetism, the AC circuits, how to put resistor in AC, capacitor in AC, inductor in AC, then inductor, capacitor in series, resistor, capacitor in series, resistor, capacitor, resistor, inductor, the 3 of them in series to make a tuning circuit, and then you can go ahead, and even make them parallel. So I didn't do much about that. Remember?
Yes.
It's your business now. Between now and Saturday. Like if you want, for your understanding of the course. And then there was a part which I thought you would read better as you prepare for E1, the part of filters, the low filter and the high filter, but we also did them in AC cycles.
Yeah.
When you were combining, so in E1, when you combine the capacitor and the resistor to kick out the AC part as you were making the ripple, which ripple was helping on getting the ripple was to, because you would end up having those who are going to do E1. And we said that on a rough estimate, you only have the DC, the actual DC being this shaded part. Now then you will render this part which is useless. And to make it useful, you needed to connect a capacitor on that experiment. And then you will end up smoothening this part here. You smoothen this part, smoothen it, but on the oscilloscope you will end up with a ripple like this, which you would have to look for the amplitude, the peak to peak, then the frequency, whatever else you got. So as you prepare for E1, I expected you to now know a thing, to remind yourself of the filters, the high pass filter and low pass filters as a section which I didn't cover so much in electronics. Otherwise, we covered the course. We covered the basics that will make you teach that, because now they have digital electronics in O level, I think, and A level. So you are now prepared to go to school and you just chop stuff and have no worry at all. So that concerning the course. I revised the test 1 about tabling, shops, superposition, and Norton, something like that. Now, I promised to do some numbers in Kanoff, but we are out of time. But also you can chop some numbers. I'd come with, if you have time, we can try to do examples. I have a whole handout of the Kanoff with a lot of examples to do, but I'm not interested in also getting tired, because I already gave you the basics on Kanoffs, which is enough for you to do any simplification using the Kanoff maps. So we did transistors, did the input and output characteristics. We did them in a test. We did them in E3, isn't it? Then E7, you did the amplifier. So you now know how an amplifier works. You saw those when we were changing just to get a peak-to-peak instead of having waveforms, remember? And you were able to now appreciate how amplification takes place. Then we went digital. D1, D2, we did the stuff. We made at least each group, including tomorrow, each group which did D1, we did the gate using the diodes. We did the gate together. We proved the truth table and eventually did the same with the chip. And then you did your stuff and managed to get these things. So that now gave us the Boolean algebra. Let's move it now. It is the notes, the other main notes are already there with enough explanation of how you arrive at the simplified part of the box you choose. There is already a typed notes there on the web, which are having all the explanation, the steps you take. And now then we digital electronics, so D1, D2. Then we did the multivibrators and multivibrator D14. At least most of you were able to reach up to when we made traffic lights, isn't it? And then you were able to appreciate that the amber, the yellow one on the road, is the monostable, which has a one stable state, so it comes on very fast and goes away. And then flip-flops, did JK, did FF, RS, set reset, and came to now conversion. Now we did conversion from digital to analog to digital, and for analog to digital we appreciated the methods in their varying speed from flash to successive, and finally to the slowest, which is dual slow. And we have added the course. And I have told you from day 1 to last day, and I apologize for when I was busy giving an error. And you grudgingly forgave me. Now, I saw some of you writing on a question paper in tests, but I had no time to quarrel. In my exam, do not write anything on the question paper apart from circling the number you are doing. Please. 1. 2. Cheating is stealing. If I get you cheating, I send you home. If the university is legal, he likes legalese, I will pack my things and go home. And I let you do your degree, your university will benefit from you. So if I get you cheating in my paper, there is no nonsense of that there is examination malpractice committee. I don't appear in that nonsense. You either go away and forget about a degree, or I will go. So don't have this, how do I call it, temptation of saying, let me, the ladies are here, they put some things on the thighs. I don't check. But if I saw you looking, and the lady says she had, we shall take the photo in black and white and make sure it will go away forever. To avoid problems, because if I take a colored one, I may be sued. We shall take a black and white. And I'll make sure that you are sent away. You are useless to the university. If you are cheating. After teaching you for this month without coaching, without ever going at it, or coming in late, and then in the lab, have I ever missed a lab session? No. I come from the beginning to the end. You even gave me flu at one point. And I suffered for some weekend, but it is okay. Those are occupational hazards. But if you have been attending, I can assure you, if you have been attending this course from the beginning to today, you will get an A in this course. Well, you may not get an A because of practicals and maybe online assignments, but you will get at least a B. If you have been attending and you read what you have been attending, you will get a B plus. Okay? So with those few words and caution, I would like to thank you for your cooperation, at least during lectures. I would like to thank you for trying to be on the weather. People like Apanwa now have like 50 days without ever going to the weather. People like Valentina, who is always on phone in the corridors, he has 40 days before when he was on wedding. People like Katoko has over 30 days. I don't know whether she's allergic to wedding. People like Sisi, who is trying to log in now, it's like 25 days ever since she was on wedding. I don't know your logic behind it. But I don't mind. It is for your own good. All the lectures, including the one I'm going to finish in a few seconds, are all going to be on video. So anytime you feel like you don't remember how I fidgeted with explaining a point, you can always go and see how I fidgeted to explain. Yes, Mugai.
How is this coursework distributed?
The courseworks are distributed with tests are out of 12. Assignments are out of 8, that's 20. The practical is out of 20, plus then you add around is 40. So exam will be out of 60. So if you got the practicals and you got your 20 out of 20, and you get a 10 out of 20 for the assignment and test, that is already 30, you'll be just looking for 20% out of the 60 to pass the course and get above average, above 50 to pass the course. Simple as that. But the lab is done. Especially for Wednesday group, we are done with practicals, so you have no chance of adjusting. Yes, Collins. I am very, how do I call it? I'm looking for a nice word. I don't want to cheat anyone. Whatever you did, you shouldn't be cheated. It should be considered. You get my point? How can I now make you not benefit from what you did? So I am too considerate that I want your efforts to be rewarded. Whatever you did, whatever you laid your hand on, should be considered. But for practicals, I think we're going to make eventually 8. or 7, so I'll try to consider 4 best done practicals. For fairness, I'll make sure, so since there were 9, and we lost 1 officially to the exam when we were extending, and there are 8, I'll chop half. So the assumption is that at least you did 4 practicals when you had an idea of the theory. So you should be judged in that form. And the evidence should be how you perform in it. So I will be looking for the best 4 done for the practicals. For practicals, I will do an illegal thing of not considering all your efforts. But for tests, you have to be, I don't want to malice you. You sit in a test and then I don't consider it. That is unfair for you, eh? So I consider all the tests. Any other query? So I will miss you for those of Wednesday who are done. I'll see you again in the exam. But I'll miss you on Tuesdays, Wednesdays, Thursdays. They will never be the same again. And so I wish you good luck in your exams, other exams, and eventually my exam. And so you can have a good night. Thank you very much.